What's up, guys? Let's get into chapter 6. So, in chapter 6, what I want to start you out was a little review for chapter 6 before we get deep into it. So, we're going to do a factoring review and a couple other reviews. I'm going to put all these up on the board at the same time, and then we'll go ahead and do all these factors. So, on your worksheet, you should have A through D for factoring, and then we'll get into simplifying. Let's go through, and I'm about to take it to the board, and we will factor A through D. Alright, let's do this review. We got A, says 3x to the third minus 21x squared plus 36x. First thing I see here is I can pull a 3 out of everything. If I pull a 3 out of everything, it makes it a little easier. So if I pull a 3 out, I can also pull an x out. So I got 3x's here, 2x's here, and an x here. So I'm going to pull out a 3x. Pull that 3x out here, it's going to leave me with x squared. Pull a 3x out of negative 21x squared, it's going to give me a negative 7x. I pull a 3x out of 36x, it's going to leave me with just a plus 12. That's 3x times 12 is 36x. 3x times negative 7x is negative 21x squared. 3x times x squared is 3x squared. Or to the third, excuse me. Alright, so let's see if we can factor this part as well, make it a little more simple. So, I know an x has to go here, an x has to go here. What times what gives you 12, but also adds the negative 7. How about a, let's see, how about a negative 3 and a negative 4? Negative 3 times negative 4 is positive 12. Negative 3 plus negative 4 is negative 7. So, this is completely factored. This is what I would be looking for as your answer if I wanted you to completely factor this particular problem. Let's do B. Do it in a different color so that hopefully you can differentiate between two. So here I've got a negative 6x to the fourth at minus 10x to the third plus x to the, or 4x squared. So here I can pull out a 2x squared, okay, because I can get an x squared out of all of these. Okay, so I'm going to do that. Something I'm probably going to do here too, just to make it easy, I like to have a positive coefficient in front of my largest x with the largest exponent. So I'm actually going to pull out a negative 2x squared. If I pull a negative 2x squared out of negative 6x to the fourth, I should be left with 3x squared. If I pull a negative 2x squared out of negative 10x to the third, I should be left with plus 5x. Okay. If I pull a negative 2x squared out of a positive 4x squared, what I should be left with is a negative 2. Okay. Now I'm going to try to factor this part here. Okay. So I'm going to rewrite my negative 2x squared. I'm going to give myself two parentheses. If you have a different method, by all means, whatever method you want to use here, there's several methods of factoring. Use whichever one you're comfortable with. Okay. So here I know I've got to have a 3x here, and I've got to have an x here, right? So I also have to have something that multiplies to give me negative 2, but adds to give me a 5 here. So I'm thinking I'm going to have a plus 2 here, and I'm going to have a minus 1 here. So that if I go through it, 3x times 3x is 3x squared. 3x times 2 is a positive 6. Minus 1x is a positive 5x. Negative 1 times positive 2 gives you the negative 2. You have another method. Like I said, this is just a review. We've already gone over this semester. We've gone through several methods of factoring. So use whatever method you're comfortable with, as long as you can get it factored completely. So C here, we've got x to the fourth minus 6x squared plus 8. Okay, so we need to factor this one. Now, this one's a little different, but it's not that much different. Okay, I'm going to split it up. I'm going to say x squared here, x squared here, because I want to split up this x to the fourth. Okay. Now I got to figure out what goes on the end. I need something that multiplies to give me 8 and adds to give me negative 6. Okay. So how about a negative 4 and a negative 2? Okay. But that's not it. Now we still have these squareds here that we have to deal with. Okay. So we need to try to factor them. So I need something that multiplies to give me negative 4 and adds to give me 0. How about a -2 and a +2? Okay. Here, same thing. I need something that multiplies to give me -2 and adds to give me a 0. Not seeing that one. So, because it's not a perfect square, it's not really going to work out. So, what you wind up doing here is you'll just leave this x squared -2. Because that part right there just doesn't factor any lower. You couldn't do a 2 and a 1 because then you wouldn't wind up with a 0 middle term. So this is as simple as you can get. This would be the answer that I would be looking for. D, x to the 4th minus 18x squared plus 81. Okay, we'll work it the same way. We'll say, okay, x squared and x squared. All I'm doing is splitting up this first term, trying to figure out the other two terms. I need two numbers that multiply to 81 and add to -18. How about -9 and -9? Okay. 9 is a perfect square, so we're going to be able to split these up. We can split this one up into x. Let's see, x minus 9. So x minus 3 times x plus 3. And we can split this one up into the same thing, x minus 3, x plus 3. Okay. What you might also see, and which is also acceptable, will be x minus 3 squared, x plus 3 squared. Because I can actually combine these two terms. That's perfectly fine as well. So depending on how it's asking you to answer, if it wants you to answer completely out like this, you might have to do that. You might also see in a multiple choice question that answer as well. That's fine too. But you got to be able to factor these. Okay. Like I said, if you have a different method, some people like to do a U substitution here. Some people have never heard of a U substitution. That's why I just jumped to splitting this term, just like we split this squared term over here when we did it. So whatever works best for you, as long as you can factor it. The next set of examples says to simplify, and we have 3 of these examples we're going to simplify. So let's take it to the board and simplify these 3 examples. Let's look at A. So what I'm going to start with on A, I'm going to pull out a 2 on top. So if I pull out a 2 on top, I get 2x squared minus 4 all over x plus 2. Okay. Now I'm going to factor this piece here. So I get 2 times x minus 2 times x plus 2 all over x plus 2. Now if you notice, I've got an x plus 2 on the top and an x plus 2 on the bottom. They're all multiplied on the top, therefore I can cancel it with the bottom. So if I come through here, what I can do is I can say, okay, this cancels with that. Therefore my final simplification will look like 2 times x minus 2. And that will be the answer I'd be looking for A. The other answer you might see something that looks like 2x minus 4. If you multiply the 2 back in, that's a possible multiple choice answer. But more than likely, I'd be looking for this. Alright, on part B. First thing I see is I can pull out a 3. Okay, so let's pull a 3 out of everything. And by that, what I mean is there's a 3x on the top, right? If I pull a 3 out of the bottom, I get a 3 times x plus 2. Okay? Now I can cancel those 3's. That 3 cancels that 3. And what I'm left with is x over x plus 2. Now you can't simplify in that any further. The thing with having something on the denominator, you're not wanting to split the denominator like that. If it was multiplied, it'd be different. But that's pretty much as simple as what you're going to see. Okay. Now let's look at C. C says 3x squared minus 14x plus 8 all over x squared minus 16. Okay, so we can try to factor the top. So if we try to factor the top, I know I'm going to have a 3x here. I'm going to have an x here. Okay, so I need 2 numbers that multiply to give me 8, and somehow that multiplied by 3 is going to add to be -14. So if I'm looking at it, the options we have, we can do a 2, a 4, we can do an 8 and a 1. So if we look at those options, if we do 3 times 8, 3 times 8 is going to wind up giving you 24. and then we're going to wind up having to subtract that from 1, and that's not going to give you 14. If we do 3 times 4, that'll give you 12, right? 12 and that negative 2, that'll probably work out. So let's look at a 4 and a 2. So 4 and a 2. Alright. So if we're looking at a 4 and a 2, 3 times 4 will give you 12. 2 times x will give you 2. 12 plus 2 is 14. We do want it to be negative, so everything has to be negative. Negative 2 times negative 4 is positive 8. Okay. If you got a different way of factoring, like I said, this is just a review. This isn't teaching factoring. So if you have a different way that can still get you there, by all means, go with it. Now we need to factor x squared minus 16 on the bottom. It's a perfect square, so it's going to factor into x plus 4, x minus 4, right? So if it factors like that, what I notice here is we've got an x minus 4 on the top and an x minus 4 on the bottom, so those cancel. What I get is 3x minus 2 on top, x plus 4 on the bottom. Okay, so we have completed it. We've got 3x minus 2 on top, x plus 4 on the bottom. There's nothing else I can do to simplify this, so we are done. So that will be your final answer for part C. This part says divide and simplify. So we've got 2 examples for it. So let's take A and B to the board and try to solve them. So let's solve A. You know when you divide a fraction, you keep, change, flip, keep, change, flip. So we're going to keep the first one. We change this to a multiply. We're going to flip the second one. Alright, now we can look at what we cancel out. So there's one A on the bottom, there's 2 A's on the top. So I'm going to cancel this 1A, change that 2 to a 1. There is a C on the bottom. I'm going to cancel it, and I'm going to cancel one of these C's on top. There's one B on top, so I'm going to cancel it, change that 3 to a 2. Alright, so what it looks like, I've got one A on top, I've got one C on top, and I've got 2 B's on the bottom. So A, C over B squared. That's it. Hopefully that one's pretty simple for you. Now B is a lot more complex, okay? So, still works the same way. We're going to keep the first one. X squared plus 7x plus 12 over 2 minus x. We're going to change the second one to multiply, and this third we're going to flip. So we get x squared minus x minus 2 all over x squared minus 9. Okay? So, what we've got to do now is I'm going to factor as many of these terms as I possibly can. And you'll see why I do that here in a second, because when I factor them, we'll wind up with some stuff that actually cancels. So if we factor this first term here, this x squared plus 7x plus 12, what I notice is I need 2 things that multiply to 12, add to 7. How about an x plus 3 and an x plus 4? Okay. All that is over 2 minus x. I'm going to pull out a negative, make that x plus 2. Or, sorry, x minus 2. Okay. So, I'm going to do it in the second one as well. So, this x squared minus x minus 2, I'm going to factor it. It's going to be x and the x here. Okay, I need 2 things that multiply to give me negative 2, add to give me negative 1. How about a negative 2 and a positive 1? Okay. And here I've got x squared minus 9. I want to factor it as well. It's a perfect square. It winds up being x minus 3, x plus 3. Alright. Now, you can see the reason I've done this, the way I've done it, and the reason that I switched this one around is so that I can cancel this with that. I can cancel this with this. Alright. And what I'll get is x plus 4 times x plus 1 all over negative x minus 3. And that's probably what I would be looking for the final answer. If you saw it on multiple choice, that is probably what the multiple choice would give to you as an answer selection choice. It might have the negative brought up top. That might be the only difference you see. Sometimes they want you to get here and refactor it back out. We're not going to do that. You're capable of factoring if they need it if you need to factor it for the final or answer in a multiple choice, you could do that. Wouldn't be a problem at all. Or you could type both of them in your calculator, see if they match, and that would work as well. So hopefully you've got this. Like I said, just review. Next section says add, and the one after that says subtract. Let's do both of these at the same time. I'm going to put both the addition one and the subtraction one on the board, and we'll solve both of them. Alright, so what we're going to do with this first one, it says add 3 over x squared y plus 5 over x times y squared. Okay, we need to get a common denominator when we add. These are essentially fractions, and to add fractions you need a common denominator. So to make this denominator look like this denominator, I noticed that I have a y squared here, so I need a y squared here. In order to do that, I need to multiply this whole thing by y over y. Now I have an x y squared here, but I need an x squared so these x's will match. So I'm going to multiply this one times x over x. Alright, if I do that, I get a 3y over x squared y squared, which will be my common denominator. Here I'll get a 5x over x squared y squared. Okay. Now I have a common denominator, so I can add what's in the numerator. So what I'm going to add is 3y plus 5x all over x squared y squared. And that's as simple as you can get that one. Let's look at subtraction. So, excuse me. Same thing I need here. That was nasty. I need a common denominator. Okay. I'm going to factor this one on the bottom. So, if I factor that one on the bottom, what I'm going to wind up with is I'm going to wind up with an x plus 3, x minus 2. That way when I compare them, instead of multiplying this whole thing over here and this whole thing over here, wouldn't make sense. Factor this one, you'll see it already has this term in it. That means I just need to take this term over here on this side, and I need to multiply this whole term here by x plus 3 over x plus 3, which is essentially 1. And then I'll have a x minus 2 and an x plus 3 in both denominators. So that what you get is x plus 1 minus 2x, and that needs to be in parentheses, 2x minus 1 times x plus 3. Okay, all over x plus 3 times x minus 2. Now we got some simplification to do here. I wouldn't want you to leave it like that. So what I'm going to do is I'm going to go ahead and FOIL this and make it in one term and try to combine everything in the numerator. Okay, so if I FOIL that top part, what I get is, I'm going to leave the negative out front for now. 2x times x is 2x squared. 2x times 3 is plus 6x. Negative 1 times x is minus x, and then minus 3. Okay, now let's simplify it a little bit. I'll go ahead and rewrite the denominator down here. Okay, and I'm running out of board space. I'm going to do it one more time here, and then we'll bring it back up to the top if we need to. So I wind up with x plus 1 minus, 2x squared. If you combine these terms, you wind up with a plus 5x minus 3 all over x plus 3 times x minus 2. Okay, I'm going to erase this addition part. Hopefully you got the answer for it already. And I'm going to continue this up top because I run out of board space. What I'm going to do is apply this negative to all these terms and kind of simplify this top part. What I get is x plus 1 minus 2x squared minus 5x, and then it'll actually be plus 3 all over x plus 3 times x minus 2. Okay, so I can combine this x with this negative 5x. That negative 2x squared is going to stay the same. So x minus 5x is going to be minus 4x. Okay, so I've taken care of that, I've taken care of that, I've taken care of that. I can combine that 1 and that 3, that's going to give me a plus 4. Okay, and all that is over x plus 3 times x minus 2. Now, I'm going to attempt to refactor this top part in hopes that maybe one of these will cancel. Maybe it will, maybe it won't. Okay, what I see is I can pull out a negative 2 on the top. That'll already make it a little easier. So that'll leave me with x squared, my plus 2x minus 2 on top, x plus 3, x minus 2 on the bottom. Now if you go to factor this, you look at this, you know, I'm going to need two numbers that multiply to negative 2 but add to positive 2. You're not going to be able to come up with anything that works like that. So two numbers that multiply to negative 2, really the only thing that multiplies to give you negative 2, that's a whole number, is either a positive 2 and a negative 1, or a negative 1 and a positive 2, and neither one of those are going to add to give you that positive 2x there. So this really is as simple as you can get it. So this would be what the final answer would look like for that one. That is a long problem. A lot of manipulating going on there to try to get you the final answer. Now, the last part of the review says simplify. We're given 1/3 plus 4 over x over 3 minus 1 over x times y. So let's take this to the board and solve this. So here's the problem we're supposed to be simplifying. Okay. So what I'm going to do first is get a common denominator for everything. Okay. So for this top part, what I'm going to do, I'm going to get a common denominator for it. Now, there's an x on the bottom here, there's a 3 on the bottom here, which means if I want this first one to match, it needs to have an x over x multiplied to it. If I want this second one to match, it needs to have a 3 over 3 multiplied to it. So when we get down here, what we get on the top is x, and then we have a 3x here, right? And then we've got plus 4 times 3 is 12 over 3x here, right? So that we can eventually put them together because they got the same denominator. All right. For the bottom here, I've got an x, y in the denominator here. I've got essentially an imaginary 1 in the denominator here. So all I really have to do here, if I want a common denominator, is multiply this first one by xy over xy. That'll give you a 3xy over xy minus 1 over xy. Okay. Now, the reason I do this, I'm actually going to bring it up top and try to avoid that nasty little reflection dot rounds about right here. So we'll avoid that section so you can try to see everything. What I'm going to do, like I said in this next step, is I'm just going to combine everything. So I've got x plus 12 over 3x all over 3xy minus 1 over xy. Okay? Now, we've essentially got a fraction here, and a division sign. So I can flip this bottom fraction and multiply instead of divide. So what I'm doing here is I've got x plus 12 over 3x. It's essentially the same thing as keep, change that to a multiply, and flip that one. So I get an xy here, 3xy minus 1 here. Okay? Now, I'm going to go ahead and do some cancellations. So I already noticed that this x here can cancel with this x here. Okay. And I think that's all I see right offhand that's going to cancel. So that what I get on top is y times x is xy. 12 times y is 12y. Okay. Now on bottom, I've got 3 times 3xy will be 9xy. Minus 3 times negative 1 is negative 3. Okay. Now, what you can try to do is you could try to manipulate and pull stuff out if you wanted to. But I don't see anything here that if you pulled it out that would cancel. So this would probably be what I would leave as my final answer. Now, in a multiple choice section, they might pull the y out to the front or leave the y out in the front. They might leave the 3 out in the front. You might have a few different options to look at there. And you can manipulate algebraically a little bit this and that to whatever the final answer is in a multiple choice section, depending on the format they want. But essentially, that's as simplified and multiplied out as you can get it. Now we actually get to start chapter 6.1. We've done the review. Hopefully it went smooth for you. Hopefully you knew how to do most of that stuff. Some of it might have been a little difficult, but hopefully you're at least able to get through it. But chapter 6.1, talk about higher degree polynomial functions. It says, in general, the graph of a polynomial function of degree n has at most n x-intercepts. Okay, if we look at the turning points are where the function changes from increasing to decreasing, or from decreasing to increasing. So basically, you're either going up and then coming back down, or going down and then coming back up. That's what a turning point is. Turning points are called local extrema points. Okay, so just like your maxes and your mins. Now, we've got two graphs we want to do here. It says graph f of x equals x to the third minus 5x squared minus 2x plus 5. So let's pull up our calculator here. Clear out whatever else you had going on there. I'm going to go to the y equals, and I'm going to type this function. It says x to the third. Make sure you get off the exponent. Minus, I believe it's 5x squared. Yep, minus 5x squared. Minus, what comes next? 2x plus 5. Okay, I'm going to zoom standard. Uh-oh, it's got invalid dimensions. I know why that is. In case you might, as well as I do, you might, if you have your stat plot on, it's going to give you the invalid dimensions. You're going to want to go turn your stat plot off. Okay. Now I can do zoom standard. Okay. And it's going to zoom for me. And what you see is that we have several turning points on this one. So a turning point's where it increases and then it decreases. So the turning point's right up here at top. So if you're increasing and then decrease, you have a turning point up here. It's called a max. If you're decreasing and then increasing, you'll have a turning point down here called a min, and that's your local extremes there. You can't see this min here necessarily on the screen, so you might have to zoom out to look at it. Oops. So let's zoom out one time, see if we can capture it. Yep, there it is. So you got a local extreme here, which is a max, local extreme here, which is a min. What you also notice here, and it kind of said it in the first part, it says, okay, right here. So the graph of polynomial function of degree n has at most n x-intercepts. So this one is a third degree function because it has a 3 right here. That's our biggest exponent on our x. What you also notice, oops, my YouTube channel. But what you also notice here, and if you want to zoom it back in, so if you want to go back to zoom standard, it's a degree 3 and it has 3 x-intercepts. Okay. Just because it is a degree something, so say it's a degree 4, doesn't mean it's going to have 4 x-intercepts. It means it's going to have at most 4 x-intercepts. Doesn't mean it has 4. It means it's not going to have more than 4. So this one's a degree 3. It actually does have 3 x-intercepts. It doesn't have to. It could only have, say, 1. But it has at most 3. Can't go over 3. Now let's look at the other function. So it says graph f of x equals negative 2x to the third plus 6x squared. So let's graph this one. So back to the calculator, negative 2x third. So y equals, we'll clear that one out, negative 2x to the third. And, oops, get back up on it. And the second part was plus 6x squared. Now if I graph this one, what you see here is it's a cubic function as well. So its biggest exponent is that 3 on the x. So it can have at most 3 x-intercepts. But what you notice with this one is it actually only has 2. So it touches here at the local extrema and it crosses here. So it's got 2 x-intercepts, not 3. Okay, it can have at most 3. Doesn't mean it has to have 3. So here it could have had, if the x-axis would have hit somewhere up here instead, it would have had 3. But here it decided to hit exactly on this extreme point, and it hit exactly right here. So it actually only has 2 x-intercepts. Now, if this was moved up a little bit further, or any further at all, it wouldn't have had but 1 x-intercept instead of 2. I hope that makes sense. So we've looked at this one. Still has its 2 turning points, right? But it also, instead of having 3 x-intercepts, because it's a cubic, it only has 2. Okay, so it could have up to 3. Doesn't mean it actually has to have 3. Here it only has 2. So a lot of times you have to look at the graph in order to find the answers to these. So now we're going to look at local min and local max. I've kind of talked over it with the turning points and stuff. So just to reiterate with the actual word definition, we've got local minimum is where the curve changes from decreasing to increasing. Local maximum is where the curve changes from increasing to decreasing. The highest point on the graph over an interval is called the absolute maximum point, and the lowest point on the graph over an interval is called the absolute minimum point. Now, there are people that really confuse absolute min and max with local min and max. So let me kind of, I think this example right here will kind of show you exactly what I mean by this. So let's look at example 1. It says graph x to the third minus 27x. Find the local min and local max. That's supposed to be a max. Where's the absolute max on the interval 0 to 3? Well, let's just look at the function overall to begin with. If I go to y equals, I've already typed mine in, x to the third minus 27x. You're going to have to do some manipulations with your zooms here. But if you graph it and you get a really good zoom on it, this is what it should look like. I think in my window, my zoom goes somewhere from -20 to +20 on the x min and max, and it goes on the y min and max from -160 to +160. So you can use those same restrictions as well if you'd like. It gives this one a really good picture so that y'all can view it here with me as well. So I have a local max here and a local min here. If I need to find it on my calculator, I can go second calculate max and min. So if I want to find my local max, I can locate my local max visually. I can go left of it, hit enter, it'll draw a bound. I can go right of it, hit enter again, it'll draw another bound, and I can guess where it's at. And the computer, what it'll do, or the calculator, what it'll do is it'll go through and it'll find it. Now what you wind up sometimes with the TI-84 calculator is it'll give you a local maximum at -2.999999 and a y of 54. Okay, go ahead and round it up to -3. Okay, it uses a computer generated function to try to guesstimate where these things are at. Instead of going through and doing the actual math, it does like a function to do it and kind of an algorithm to do it. So sometimes it rounds like this or estimates and it gets really close, but it doesn't round it to the correct one. The correct point here is -3 and y equals 54. So we have a local max. So I'll pull it up. This is a local max. Let me go on ahead and write it on here. So I'm going to hit this. So we have a local max at -3 for your x, and our y here, just to verify, was 54. So that was our local max, and that's what it was asking for here. That's my correction for max. Okay, make sure we close my parentheses. So if I want to find my local min for it, what I'm going to do, I'm going to do the same thing. I'm going to do second calc, and I'm going to do minimum. Okay, so what it'll do, it'll start here. I'll go somewhere over here and kind of bound it, and then I'll guess where it's at. And the calculator will say it's at 2.999999 and y equals -54. Okay, so what it's really saying is, like I said, it uses an algorithm instead of being precise. So what it's going to do is, our minimum is at 3 -54. So our local min here is at 3 -54. And that's the answer for part A. So we have located our local max and our local min. Now if we look on this, it says what is the absolute max on the interval from 0 to 3. So I come over here to my calculator, I do window 0 to 3 on my x, and I graph. Okay, my local max here is going to be my highest point. Okay, or I'm sorry, my absolute max is going to be my highest point. Okay, we don't have a local max or a local min here. All we have is what almost, it's not a straight line, but we've got a curved line here, right? We have no local extrema on this interval. So our absolute max is going to be where this line is the highest. Okay. Now to find that, it could be a little more difficult, but we do see it's right here at the 0 point. So what I can do is I can go second table, right? At my 0 is where I'm my highest. So the highest point on the range from 0 to 3 here is actually just that 0, which we kind of can confer by looking at the graph. So the answer here that we would use for this, where is the absolute max on this interval? It is at 0, 0. So an absolute max can be a local max or a local. So an absolute max can be a local max, but it doesn't necessarily have to be a local max. In this example, on this interval, it's not a local max. It's just the highest point. Okay. An absolute min can also be a local min, but it doesn't have to be. It could just be the lowest point. So you keep that in mind. Absolute max and absolute min aren't the same thing as local max and local min. I see a lot of people get tripped up on that. Example 2. Example 2 says the number of millions of elderly in the workforce for the years from 1970 and projected to 2050 can be modeled by the cubic function y equals, and it gives you the cubic function. I'm not going to attempt to read it out because I'm going to wind up stuttering a little bit. But you can see it right there on your paper, where x is the number of years after 1960 and y is in millions. A says use the model to predict the number of elderly workers in 2025. Okay, so let's do that. Okay, I'm not going to do this by hand. I'm going to do it using the calculator. So all I've got to do, I'm going to bring this over to the side, and I'm going to bring this up here, and I'm going to type this function into my calculator on y equals. So I've got negative 0 point, and we've got 4 zeros after that, 597 x to the third. Then we've got a plus 0 point, got 2 zeros, 934 x squared. Okay, then we have a minus 0.308 x plus a 5.63. And I don't think I'm missing anything else with that. So that's the function. We want to use the model to predict the number of elderly workers in 2025. X is the number of years. So we have this typed in. If you want to hit graph, you can. No telling how it's going to show up on the current window. We'll work on that in just a second. But going back to the problem, okay, it says use the model to predict the number of elderly workers in 2025. Okay, X is the number of years after 1960. So how many years after 1960 is 2025? Pull the calculator up. 2025 minus 1960 means the x value that we should use is 65. So here we want to use x equals 65 for part A. Okay. Now let's get a decent graph of this going. So I pull my graph back up, make it larger. I'm gonna do zoom. I'm gonna do zoom standard, which I know is not gonna do the greatest job graphing this. But then after zoom standard, I'm gonna do zoom fit. The reason I do zoom standard is it brings your window kind of back to normal before you start manipulating with it. Now that I've got it at a zoom fit, it didn't do a really good job either. If I go back to zoom standard, I might be better off just zooming out. So zoom standard, then follow it up with a zoom out, which is 3. And you can zoom out as many times as necessary. Now, I think I zoomed out 2 or 3 times there. You can see the curve here. I think we're good with it. Okay. Now, if we want to find, so second calc value when x is 65, so we can answer part A. When x is 65, y is 8.6763875. Let's round it to 3 decimal places. So y is 8.676. 8.676. So y is in millions. So that's also important to note. So your answer to A would be 8.676 millions. Okay. So that'd be 8.676 million elderly workers in 2025. B says use technology in the model to estimate or define the year in the period from 1960 to 2060 during which the number of elderly workers is expected to reach its maximum. Okay. Now, what I'm going to do, 1960 is year 0. 2060 will be year 100. Okay. So I'm going to bound my x between 0 and 100. What I mean by that is I'm going to come over here to my calculator. I'm going to do window. And I'm going to bound it from 0 to 100. Okay. And then I'm going to graph it. You can see the graph really doesn't look really pretty at that point. But what I can do after I do that is I can do a zoom fit. And what it does is it preserves my x-axis here. So if I go back to my window, my x-axis is preserved from 0 to 100. But it zooms the y appropriately on that 0 to 100. So that I get a really, really nice graph here. Now it wants to know the maximum between 0 and 100. We have it bounded correctly. Looks like the maximum is going to be up here. Luckily, this is actually a local max. Is going to wind up being our absolute maximum here. So all I have to do to find it, I can go second calc. I can do maximum, which is number 4. Okay, we need to bound it to the left and bound it to the right, and then guess it. So I'm going to bound it to the left here. Doesn't have to be exactly where I bounded it. It just has to be somewhere to the left and somewhere to the right. I'm going to bound it there, and then I'm going to guess that it's right here. Okay, and it tells me it has a maximum at x equals 83.77 and y equals 10.27691. Okay, so x is our number of years. So if we go back to the question, it says use technology in the model to find the year in the period from 1960 to 2060 during which the number of elderly workers is expected to reach its maximum. So we need to find the year. Okay, the year is our x. If I'm looking at this, my x here is 83.77. So what I'm going to say is 83.77 plus 1960. So 1960 plus 83.77. Okay, that means in year 2043.77 is when I'm going to have my maximum. I'm going to round up. That's what that 7 tells me to do, is round up. So I'm going to round up to year 2044, and that's going to be my answer. So that's our answer for B. So let's look at part C. Part C says a local minimum occurs at 20.5, 2.73. What does this function do on the interval from 20.5 to 83.8? Okay, so if I come over here to my graph, look at it. Okay, so this, if you wanted to, you can hit the trace button to kind of get an idea. So this minimum, we said, and you can find it exactly in your calculator if you want to. You cannot find a minimum exactly with trace, but essentially right here where this minimum is at, between it and this 83 something up top, which is essentially where this maximum is at, right? So it wants to know what it does there. Well, it's a pretty simple question. So from here to here, it increases. That's it. That would be your answer, part C. So what does the function do on the interval from this point to that point? It increases. And that will be the answer C. Next part of this chapter is quartic functions. So a quartic function is essentially a function that has an x with an exponent of 4. Okay, so that your general function looks like f of x equals a times x to the 4th plus b times x to the 3rd plus c times x squared plus d times x plus e. Okay, so we've got a few examples. Here it says graph and state the number of turning points. Okay, so f of x equals x to the 4th. It's a very simple one. Let's graph it. F of x equals x to the 4th. X to the 4th. Now I'm just going to zoom standard on it. Hopefully it'll show up nice. Okay, looks like there's only one turning point. I caution you to be careful. Maybe do some zooming out to be sure. Okay, and what I notice is that when I zoom out, it doesn't really look like anything changes. So you can zoom fit if you want to as well to try to get a better picture. But really what you see is it's got one turning point. It's got what is a minimum right here, right? So it's got one turning point. That would be your answer for this. Graph and state the number of turning points. This one has 1. Okay, let's graph the second one. X to the 4th minus 3x squared. So y equals x to the 4th minus 3x squared. Okay, now I'm going to zoom fit this one to you. Okay, doesn't look much different. Let's be sure. Let's zoom standard. Make sure we're not missing anything. See, you got to be careful with your zoom, because when I zoom fit that one, didn't really look like much of anything. Looked like I have one minimum. But when I zoom standard on it, what I actually see is it's got several turning points. It's got a turning point here, and one there. Okay, so this one actually has 3 turning points. So if I come over here, how many turning points does this one have? It has 3. Okay, let's look at 3x to the 4th minus 4x to the 3rd. Three x to the 4th minus 4x to the 3rd. Okay, if I graph this one, what I can see is it does something kind of funny. Okay, and if you want to get a little better view, you can try to zoom in on that funny looking spot and see exactly what it does. But what you see when you zoom in is it starts to go down, and it almost creates a turning point here, but it actually continues to decrease so that you actually only have one turning point on this graph. Okay, so even if you continue to zoom in here, what you'll notice is there's a steady decrease here, even though it slows down. What happens here is because you have this cubic function within this quartic function. Let me see, I'll go back to zoom standard. Because you have that cubic function in that quartic function, essentially this little swing part here is the cubic part, and then it comes back up and turns it back into a quartic part. That's the best way I can describe it, really with words. So that if you've ever seen, and I know you have because you've been in this class obviously, if you've seen a cubic function, it does exactly like this does. It goes down and then it comes back down. The only difference here is it's got that extra quartic part which actually makes it swing back up. So here, how many turning points do you have with this graph? You actually here only have 1 as well. So you have to be really, really careful. All that leads us into these few statements here. So if we're looking at polynomial graphs, the graph of a polynomial function of degree n has at most n minus 1 turning points. So it doesn't mean it has n minus 1 turning points. It means it has at most n minus 1 turning points. Just like that degree 4 we looked at. Depending on the graph of the degree 4 function, it could have 3 turning points, it could have 1 turning point, it could have 2 turning points. Okay. 2 says the graph of a polynomial function of degree n has at most n x-intercepts. We've seen that as well. Okay. Just because it's a cubic function doesn't mean it has to hit the x-axis 3 times. It can hit it at most 3 times. Okay. It might only hit it once. Okay. Now, 3 says the end behavior of the graph of a polynomial function with odd degree can be described as one end opening up and one end opening down. Okay, so you've seen that with cubic functions, and if I show you a basic example here, like I said, of a cubic function, x cubed, so x to the 3rd, what you notice is one end goes up, one end goes down. So any odd numbered function with an odd exponent on your largest x is going to have that kind of end behavior. One end's going to go up, one end's going to go down. That's your odd ones. Your even ones, the end behavior of a graph of a polynomial function with an even degree can be described as both ends opening up or both ends opening down. So that makes sense. If you look at one as simple as x squared, you can see that. So both ends open in the same direction for an even number function. Here they both open up. If you change it around, you want it to be something a lot more complicated, maybe an x to the, I don't know, another even function, x to the 10th. What you see, still both ends in the same direction. So they either both go up or both go down. All right. Do example 3. Example 3 says figures 6.7 a through d show the complete graphs of several polynomial functions. For each function, determine a says the number of x-intercept, b says the number of turning points, c says whether the leading coefficient is positive or negative, D says whether the degree of the polynomial is even or odd. And E says the minimum possible degree. Okay, so we have 4 of these, A, B, and C to look at. Okay, let's look at A first. So the first thing we have to do for A is figure out the number of x-intercepts. So how many times does it hit the x-axis? 2. So for A, for the first one, the answer to A would be 2. For B, for the first one, it says the number of turning points. Okay, looks like it only has 1. It goes down, then it comes back up. So it's got 1 turning point, right? C, for the first one, says whether the leading coefficient is positive or negative. Now, what I tell people is if you can't remember, just go graph something, right? The ends go in the same direction. It has to be an even exponent, right? So go graph an even exponent. We've got one already graphed, right? So these ends both go up. So if you can't remember, here I have a positive coefficient. Positive coefficient is 1, right? So when I have a positive coefficient, they both go up. So if I have a negative coefficient on the converse, so if there would have been a second insert negative 1 here instead of a positive 1, you'll notice that both ends go down. So what you have here is you have a positive. So I'm just going to write POS for positive. So you have a positive leading coefficient. D says whether the degree of the polynomial is even or odd. Obviously, the ends go in the same direction. It's going to be even for this one. So let me scroll down some. D, oops, got my cursor. So D for this first one would be even. Okay, last one, E. What is the minimum possible degree here? So because we only have 1 turning point, the minimum possible degree for this one is a squared, right? So the smallest it could be is a squared. It could be bigger than a squared, but the smallest it could be is a squared, okay? So let's answer these same questions for part B. So A, if we go back up, recall what A asked. A asked the number of x-intercepts. So here it intercepts here, here, and here. So we have 3 x-intercepts. B asked the number of turning points. So we have a turning point here, here, and here. So we actually have 3 turning points as well. C says whether the leading coefficient is positive or negative. Well, and we can kind of combine this with D as well. Is it even or odd? So it's an even function here. My ends are both in the same direction. It's an even function. Sometimes it might be easier to answer D first so that we can figure out the leading coefficient second. But it's an even function here. C wants to know, is it positive or negative? Well, we already know if it goes up, it's positive for even coefficients. If it goes down, it's negative for even coefficients. So it's a negative leading coefficient here. E, for this one, the minimum possible degree here. So the easiest way to think about this, okay, it's an even, right? We're looking at the number of turning points, which is n minus 1. So n plus 1 would actually be a 4. So the minimum it could be is a 4 here. I hope that made sense. So if you look at your turning point formula, how we got B, okay, the turning point formula, the most turning points you can have is n minus 1, right, of your coefficient. So if you kind of reverse that, if you know that you have 3 turning points, the most or the smallest that your degree could be would be 4. Couldn't be 2. Remember, 2 is just kind of straight like that. It has to have some turning points in it, so it'd be a 4. Alright, let's complete C and D as well. So A for part C. If I scroll up, recall what A asked. A is the number of x-intercepts. B is the turning points. So here, X hits once. So there's 1 here. B is the turning points. Okay. Does this one have a turning point at all? This one doesn't have a turning point at all. Okay. Okay. So it's always constantly going down. So there's no turning points to it. Now C wants to know, is the leading coefficient positive or negative? If you can't remember for odd exponents, do something simple. graph an x to the third and see what it looks like. Okay, x to the third has a positive coefficient on the front of it. If we graph it, we notice that it starts down and then goes up. So that's with a positive. If you wanted to look at the negative one, you could insert a negative one here, and you'll see that if it has a negative coefficient, it goes down. Okay, so if we're looking at this one goes down, so it has a negative leading coefficient. That's the easiest way. If you're having trouble remembering the number, you can actually work through it on the calculator because you have a calculator to work through it with. Now, did I answer that correctly? Yeah. So D is the one that asks, is it even or odd? Okay. The end behavior is in different directions. Here the end behavior is up, here it's down. So we know it has to be odd. And E asks, I believe, what is the smallest one that it could be here. Here, the smallest one it could be would be a cubic. And I think you can see that pretty easy. Looks just like a cubic. So if we answer this one for the very last one, A wants to know the number of x-intercepts. This one has 1, 2, 3. Okay, we've got 3 x-intercepts here. Alright. B wants to know how many turning points we have. We have a turning point here. We have a turning point here. So we have 2 turning points. C wants to know if it's positive or negative. Okay, starts down, goes up, it's positive. Okay. We look at D. Is it an even or odd function? The end behavior is in 2 different directions, so it's an odd function. And the lowest possible degree of this function is still 3. So E is still 3. Hopefully those are meant to be really, really simple. Hopefully you were able to get that. Example 4 says using data from 2000 and projected to 2015, the function y equals, and it's a long function, it's a quartic function, can be used to model the U.S. unemployment rate with x equal to the number of years after 2000. A says graph the function for x values from 0 to 15. So let's do that. Now, I've already typed the function in on my calculator here. Okay, so take your time and pause here if you need to type it on your calculator. Make sure you type everything in correctly. It's a very long function. Now, if we just do a regular zoom standard, what's going to happen here is it's going to graph about like that. What A wants us to do is to graph the function for x values from 0 to 15. Okay, so what we need to do, we need to go to the window, and our initial x is 0, our x min is 0, our x max is 15. If we do that and graph it, what we see here is we've got a function from 0 to 15, and you know, we've actually, with the initial standard view, if you started with the standard view, once we do this boundary difference here from 0 to 15, it shows up rather well. Okay, so we've graphed the function for part A. We've done part A. B says use the graph and technology to approximate the year after 2000 in which U.S. unemployment is a maximum, and the year after 2002 and before 2015 in which it is a minimum. Okay, so we want to figure out the maximum first. If I come over to my calculator, we have a maximum right here. That's an easy one to find. So if I go second calc maximum, our local maximum will be our maximum here. So I'm going to go left bound of it and give it a bound. I'm going to go right of it and give it a bound. And then I'm going to go right about where I think it's at, hit enter, and the calculator will find it. So at x equals 12.296961 and y equals 9.4899 is where we get our maximum. Now, it says we want to approximate the year after 2000 in which U.S. unemployment was a maximum. Okay, so we need to add whatever our x value here is to the year 2000. Our x value here is 12.296. If we round to the nearest year, I'm going to round it to 12. So 12 plus 2000 will give you the year 2012. That's where our maximum's at. So that's going to be our max for part B. Now, it wants to know between the year 2002 and before 2015, which is the minimum. Okay, so if I pull this up, 2002 would be about right here at this 2, right? 2015 is obviously all the way over here on the end. Now it looks to me like there is perhaps a minimum somewhere along here. So let's see if we can find it. Let's go second calc. Let's see if there is a local minimum here. There may be, there may not be. So if we go left of it, right? So we want to go left bound x equals 2, or as close to 2 as we can get. So we'll say there, right bound, maybe we'll just go to where it starts increasing. And we'll see if we can find a local minimum here. We might not be able to. There might not be one here. But it does find one. So if you go somewhere close to 2 and then somewhere over here before it starts to increase, you actually do find a local minimum at x equals 3.92. So approximately 4. Okay, so if we come back over here, it says we want to know the year between these two, which is the minimum. It would actually be the year 2004 is when unemployment was the minimum. Because we had to add that 4 to 2000 because 2000 was our initial year. C says, is it likely that this model can be used to estimate U.S. unemployment rate for long after 2015? Okay, well 2015 is here. Now if we want to do something kind of simple and just zoom out just a little bit, okay, so I'm going to kind of center it up first, maybe even go a little bit to the right because we're worried about 2015. If we notice, right, so if you kind of scroll your X around to somewhere near 15, it doesn't even necessarily have to be on the graph, but here's 2015. A few years after that it goes negative, right? Well, you can't have negative unemployment. The lowest unemployment you can have is 0. So after the year 2015 you don't have much more time to actually use the model before the model becomes something that doesn't even make sense. So is it likely the model can be used to estimate U.S. unemployment rate long after 2015? I would definitely say no. If you wanted a reasoning, a few years after 2015, it becomes negative, and the lowest the unemployment rate can be is 0, so it can't be negative. So it wouldn't make sense to continue using that model. Example 5 says, use the given graph of the polynomial function to A, estimate the x-intercepts, B, state whether the leading coefficient is positive or negative, and C, determine whether the polynomial function is cubic or quartic. Okay, these should be pretty easy. A, we want to estimate these x-intercepts. So we got an x-intercept here at -2, at 1, and at 2. So -2, 0. We've got another one at +1, 0. And we've got another one at 2, 0. So those are your x-intercepts, written in coordinate notation. Okay. B says we want to know, is the leading coefficient positive or negative? So we start negative and go positive here. So this one's actually positive. And if you want to check that, just type a cubic function into your calculator, one with a positive exponent, one with a negative exponent, or not exponent, leading coefficient, one with a positive leading coefficient, one with a negative leading coefficient, and you'll see that this is indeed about the same as the one with the positive coefficient. Alright, that being said, I've already given you the answer to part C in saying that this is indeed a cubic function, right, because a cubic function is an odd numbered function and the end behavior here is different. So therefore we know it has to be a cubic. Quartic function is an even function. Cubic function is an odd function. This one's an odd function. Okay. If we do the same thing for this one, so the answer to part A, we're looking at x-intercepts. This one also has 3. So we're looking at -1, 0. We are looking at 1, 0. We are looking at 5, 0. Okay. For B, is it positive or negative? Here we start positive, go negative, therefore it is negative. It's a negative leading coefficient. Is it cubic or quartic? It's still a cubic here. And the shape just looks like a cubic. You should be able to tell cubic from quartic by just looking at the shape, honestly, or the end behavior. We do the same thing for this one, the very last one. Okay, so looks like negative 1.5, so negative 1.5 is what I'm going to say, will be our x-intercept on this left-hand side. So negative 1.5 comma 0. And on the right-hand side, it looks like a positive 1.5 comma 0. So that looks like our two x-intercepts there. We only have two of them here. It wants to know, do I have a leading coefficient that's negative or positive? Here it's positive. And C wants to know, is it cubic or quartic? I think it's pretty easy to see. The end behavior goes in the same direction. It's obviously quartic. So you should be able to look at the functions by now and tell what they are. You can use your calculator to draw you out an example if you need to. Always use your resources if you can, that you're allowed to use. And you should be good to go. I believe that's the last example with this chapter, or this part of this chapter. We will continue on with lessons 6.2 and 6.3 next time. I'll combine both of those because they're reasonably short. If you have any questions, please let me know. Send me an email. Other than that, I hope y'all are having a good time with this and figuring all this out. Hopefully it's not too hard. And I'll see you in chapter 6.2 and 6.3.